Hello, calculus kids. This will be our video over 5.1. Before we talk about what 5.1 is covering, I first want to do some bell ringers just to help us review some things. So for this first problem, it says find the derivative of the following expression. Not the anti, just the regular derivative. And some of you are looking at this and you're probably realizing this is the type of problem where I have to do the orange peel rule. So in other words, treat this parentheses and the power of 3 like your orange peel, and let's go from there. So first, let's derive the orange peel, where you'll take the power to the front and multiply it. And remember, the 2x plus 1 does not get derived yet. That gets derived later. For now, you just got to multiply that 3 to the front, and then you subtract 1 from the original power. Not 2. Subtract 1 from the original power and you get 2. So that's when you do the orange peel. Then over here, then you'll derive the slices. Basically, after you're done peeling the orange peel, you can go ahead and eat the slices. And the slices are inside the parentheses. So now you can derive this. You derive the 2x, you get 2. You derive the plus 1, that's just 0. But of course, you don't really need to put the plus 0. So once you've derived the orange peel and once you've derived the slices, then you multiply both parts together. In this case, it looks like the only things we can multiply are the 3 and the 2, which will multiply to give you 6. And then the 2x plus 1 squared, we can't really do much with that, so we'll just leave it as is. So 2x plus 1 all squared. And that would be the derivative of your function. So that was just a refresher on the orange peel rule. I wanted to refresh you because we will be using this in today's lesson. There is another refresher I want to cover real quick. So let's say you want to find the derivative of this expression. Give me a sec. I wish they would turn those off. But anyway, back to what I was saying. Say we have to find the derivative of this expression. And you'll notice that it is a fraction or quotient, which means we will have to do the quotient rule. So if you need a refresher, for the quotient rule, it is low times d high. So low d high, then minus high d low, and then bottom squared. And then you're ready to go. All right? And of course, if you need a refresher on what's low and what's high, the top part is the high, the bottom part is the low. So just a refresher, let's go ahead and try it. So first we're going to have low, and then times derivative of the high. Derivative of the high is 1. Then minus the high, which is x, times derivative of the low. Derivative of 4, in this case, is just 0. And then you can go to the bottom. In other words, take your bottom part and square it. All right, now we've done all the steps. Now you just need to simplify. First, do 4 times 1 to give you 4, and then minus x times 0, which is just 0. And then on bottom, 4 squared is 16. Well, this one actually is going to turn out pretty nice. On the top, 4 minus 0 will give you 4. So you have 14 over 16, which if you reduce that, that's just going to give you 1/4. That one was a really nice derivative. But anyway, the main objective was to refresh you on the quotient rule, because there will be a couple examples where we'll have to use that. So just keep that in mind. And now let's talk about the main topic. The main topic for 5.1 is the natural log function and how we're going to derive it. Or in other words, I'm going to be showing you how to derive the natural log ln x. And you probably have noticed that since they call it the natural log, they would originally, you think it would call it like NL x instead of lnx. But for some reason, they decided to switch the L and the N around, so it's the log of natural instead of natural log. Again, I do not know the rules behind that or why they decided to do that. That's just how it is. But anyway, our main objective is how to derive these ln natural log functions. And on the next slide, I'll show you the basics behind it. So basically, anytime natural logs, if you need to derive them, they have a unique property when it comes to finding the derivative. A property that's different from differential rules that we are familiar with. Nah, I really didn't need to say that sentence, did I? But anyway, basically what's really special about the natural log is that it really only involves what you have inside its parentheses. And basically what you do is you first derive what's in the parentheses, or in other words, find the derivative of that. And then once you have that, you're going to divide it by its original equation. Or in other words, since in this case the original was x, on bottom you would put x. And underneath that I have a more layman's terms of how to do it. Basically, you're only going to focus on the blob inside the parentheses. First, what you'll do is you'll derive the blob, and then whatever that is, you'll then divide it by what the blob looked like before you derived, or in other words, the original blob. If you think of it that way, natural logs should be a piece of cake. Let me give you some more simple examples first to show you how it goes. So let's say we're going to be deriving these four natural logs using the rule I just explained. Let's take a look at the first one. So if we need to derive or take the derivative of this, we only really need to look at the x. The first thing you're going to do is derive that x, and the derivative of x is 1. But then once you have the 1, you're going to divide it by what the function looked like originally, or in other words, just divide it by x, because that's what x looked like before you derived it. And once you have that, since there's nothing else to simplify, you're done. That's the derivative. Piece of cake. Go ahead and do a couple more of these just so you can get familiar with it. Let's move on to this one. So if we need to derive this natural log, just look at the inside. First thing you're going to do is derive x to the 5th. So multiply that to the front, that'll give you 5x. Take 1 away from the original power, and that'll give you 4. So there you go, that's the derivative. But you're not done. You're then going to divide it by what the inside looked like originally, or in other words, x to the 5th, because that's what it looked like before you derived. So there you go, you've done the derivative, now you just need to simplify. You'll notice that we got x to the 4th over x to the 5th. That means we can take out 4 x's away. So 4 x's away, that's done from there. Take 4 x's away from this, and you just have 1 power left on bottom, which simplifies that to just 5 all over x to the 1. Or if you just want to write over x, that is also acceptable. Do a couple more just to get more comfortable with it. So now this one, again, to derive this first, look at the inside, find its derivative. Multiply that 3 to the front and you'll get 6. And then your new power will be 1 less. Once you have the derivative, you then divide by the original. And the original was 2x cubed. So 2x cubed. Simplify from there. The 6 and the 2 can both be reduced by 2, which will just give you 3 over 1. And then you got x squared over x cubed. That means you can take 2 x's away. So that's gone. And then here, you're just going to have x to the 1. So all x's are gone on top, x to the 1 on bottom, which of course simplifies down to just 3 over x. There you go. All right, one more. same procedure, only focus on the inside. Derive that. 7 times 3 is 21. And then 1 less of the power, which will be 6. Then divide by that original function, which in this case, the original was 3x to the 7th. Simplify from there. The 21 and the 3, that can reduce, which will give you 7. And then x to the 6 over x to the 7, you can take 6 x's away. 6 away from there, 6 away from here, which leaves you with 1x left over, left on bottom. I think some of you are recognizing a pattern here. For all of these examples so far, it's like it always simplifies down to where you have a single x on bottom. Now, that's not going to be true for all the cases. For the simple cases, that's usually the trend, but don't assume that. Just wanted to point that out. Let's do a couple more easy ones. Now take a look at this one. So again, for this, you always take a look at what's inside. And then to derive it, or to differentiate this whole log, first take the inside and derive it. First, you'll derive the x, which will give you 1. Then derive the 2, or the plus 2, which will give you plus 0. And then from here, once you've done that, you divide by the original. And the original is x plus 2. Simplify from there. 1 plus 0 on top is just 1. And on bottom, you have x plus 2. And there you go. You see, this time, the bottom wasn't just x this time. So you can't assume the bottom will always be x. So just wanted to point that out. Let's do the same thing for the second one. If we need to find the derivative of natural log of x squared plus 4, first just take the inside and derive that. Derivative of x squared will be 2x. Derivative of 4 will just be plus 0. There you go. And now you'll divide by the original, which will be x squared plus 4. Of course, if you simplify this, x squared, or 2x plus 0 on top is 2x. And on bottom, we'll have x squared plus 4. Now, some of you are probably tempted to try and cancel out an x from top and bottom. Like, in other words, take out an x out from here and just take out an x from there. I'm going to tell you for this particular example, you can't do that. The reason why is because of this 4. We would be able to cancel out an x if the 4 also had an x. So in other words, we could take out an x from all 3 parts. But if you cannot take an x out from all 3 parts, you cannot take it out at all. So, with that said, we just have to leave it as is. You can't take out an x from everything. You better just leave it. And there you go. All right, let's take it up a notch. Let's take a look at the next example. Differentiate the following functions. Oh boy, some of you are probably already seeing the product rule on the right side. And you probably see why that's up here. Because we got a factor here, and we got a factor here, and they're being multiplied. Multiplied means product, which means to derive this, we got to use the product rule. I know I didn't go over this one in the bell ringer because I figured the product rule should be a lot easier than the quotient rule or the orange peel rule. I feel like you guys got the product rule pretty down pat. But again, we'll just walk through it just so you got a good refresher. So again, the product rule, A prime B plus B prime A. Product rule will save the day. Sorry, I had to sing that to myself. But anyway, so first, A prime, derivative of A. So take the A, find the derivative, that'll be 3x squared. And then A prime times B, where we just take the B and leave it as itself. So natural log x squared. And then plus B prime. Now we gotta take the B and find its derivative. And notice how it's a natural log. And remember, with natural logs, you just focus on the inside. So in other words, let's go ahead and set up our fraction. On top, we'll derive the x squared to get 2x. On bottom, we'll put the original, which the original was just x squared. And again, the natural log is gone at that point. You don't need it anymore once you do the b prime. And then last, we'll just put the regular a, where the regular a is x cubed. All right. We've done a prime b plus b prime a. Now we just need to simplify. Over here, 3x squared times natural log of x squared. I know some of you might be tempted to multiply that and put 3x to the fourth. Sadly, that is not the case, because the x squared in parentheses here is basically stuck to the natural log. You can't separate it and multiply it to this. And the opposite is true. You cannot take the 3x squared and multiply it to something to the x squared. They're basically two separate entities. So in other words, you have to keep them separate. So the best thing you can do is just put 3x squared times natural log x squared. That's all you can do for that part. On the other side, however, there's no natural log keeping these two from multiplying, so let's multiply these together. I'm going to go ahead and rewrite the x cubed as x cubed over 1, and then I can just multiply horizontally. If you multiply the top, 2x times x cubed, that'll give you 2x to the fourth. On bottom, x squared times 1, that will just get you x squared. And of course, some of you are recognizing we can still simplify from here. The 3x squared, natural log x squared, that stays. But for this part, you can take out 2 x's. Take out 2 x's from here, that's gone. Take out 2 x's from here, that's going to leave you with a squared. So honestly, we're really left with just 2x squared on top, and on bottom, everything cancels out down to 1. But at this point, you don't really need that 1 on bottom, so you can just write 2x squared. And there you go. That would be your derivative once you do the product rule. So just product rule, same as always. You just had to use a little bit of natural log with it. Simple as that. If you want to, go ahead and try this one on your own, doing the same thing. Make this a, make this b, then do a prime b plus b prime a. Go ahead, pause the video, and try it now. All right. Guys should have tried it by now. I'm going to go ahead and do it real quick. So first, a prime will give you 2. And then b, that'll just be natural log of x, plus b prime, which means we got to take the derivative of b. And of course, it's a natural log, so you got to use your natural log rule. On top, derive the x, which is 1. On bottom, put the original, which the original was x. And then last but not least, a prime b plus b prime a, where your a, just the regular a, is 2x. Simplify from there. Again, you can't for here. The 2 times natural log of x, you can't multiply the 2 and the x together. The x is with the ln, the 2 is not. So you have to keep them separate. So that'll be 2 natural log x. Over here, you can do the 2x and write it 2x over 1, multiply horizontally. And then on top, 1 times 2x will give you 2x. X times 1 on bottom will give you x. Simplify from there. 2 natural log x can stay as it is. But here, your x's cancel out because just 1x and 1x, you can cancel those out. And you're just left with 2 over 1. Or in other words, just 2. And that would be your derivative of that equation. There you go. So that's product rule. Simple enough. Now let's do some examples where you have to use the quotient rule. Again, we've already reviewed the quotient rule, low D high, high D low, bottom squared, ready to go. So let's go ahead and apply that to this one. So this one, here's your high, and then here's your low. Let's go ahead and set it up over here. So first, we got to do the low. Your low is going to be x. Then low D high means we got to do derivative of the high. And the high is a natural log. And do as we've always done with a natural log. First, derive what's inside. Derivative of x is 1. And then divide by the original. And the original is x. There you go. So low D high minus high, where the high is just natural log of x, and then D low, where the derivative of low is just the 1. So you go, low D high minus high D low, and then bottom squared, where your bottom is x. There you go. Now we just got to simplify. Well, first, over here, I'm going to rewrite the x as x over 1. So that means I can multiply these two fractions. And that is going to give me x times 1, which is x. And then on bottom, I'll also have x. And then minus natural log of x times 1. Well, multiplying anything by 1 doesn't really change anything. That's just going to give me natural log of x. And then bottom squared, which is x squared. Now, some of you are noticing I have x divided by x over here, which means I can simplify the x's. Now, I bet some of you are probably saying, oh, I can just cancel that out, and that's just going to leave me with negative natural log of x over x squared. Some of you are probably thinking this is what your answer is going to look like. And I'm going to tell you, you're overlooking something. Real quick. How about instead of using x divided by x, what if I gave you 5 divided by 5? If you did that, would you say 5 divided by 5 would cancel out and just give you 0 and basically disappears? You guys know better. 5 divided by 5 doesn't cancel out to become 0. It simplifies down to 1. So 5 divided by 5, or 5 divided by itself, simplifies down to 1. X divided by x follows the same rule, where if you take anything divided by itself, it simplifies down to 1. That is something a lot of kids miss. They'll just instantly cancel out and just say, oh, it's gone, it's 0, we don't need to deal with it. You got to be more careful than that. Got to remember your division rules. So that will come to 1 minus natural log of x plus 2. Put a star next to that example. That is something that a lot of kids might mess up on. Anytime you have x divided by x, that becomes 1. All right. If you have any questions about that, you know you can always email me. So that was the thing I wanted to stress about. But everything else should look good. So now, if you want to, go ahead, try the quotient rule on this example. Go ahead and pause the video and try it out. And then check your answer once you resume. All right, you should have resumed the video by now. Let's go ahead and walk through it to see if your answer matches. So this will be the high, this will be the low. So let's go ahead and do the quotient rule. So first, I got to have my low, which my low will just be natural log of x. Low and then d high, derivative of the high, which will be 4x cubed. And then minus your high, where your high is x to the 4th, and then derivative of the low. Derivative of the low. Now remember, anytime you do the natural log, just focus on the parentheses. So first, derive the parentheses. Derivative of x is 1, and then divide by the original. And the original is x. So there you go. Low d high minus high d low, and then bottom squared, where your bottom is just natural log of x. All right, let's simplify. So here we have natural log of x times 4x cubed. Now, again, you cannot multiply that to get 4x to the fourth. The x is with a natural log. The 4x cubed is not. So that can only be multiplied to the front. It cannot be multiplied with the x. So you have to leave that as 4x cubed times natural log of x. And then over here, I'm going to go ahead and rewrite x to the fourth as x to the fourth over 1. And I can multiply the two fractions. On top, I'm going to get x to the fourth. On bottom, I'm going to get x. And then all of that, all over natural log of x, all squared. All right, we can still simplify a little bit more. I'll still have 4x cubed natural log of x minus x to the fourth divided by x. Take 1x away from top and bottom. That will just leave you with x cubed over 1, which is just x cubed. And then on bottom, you can have natural log squared, but if you want to formally write it so that the squared is right in the middle, that is also correct. Basically, this notation and this notation mean the exact same thing. I just like to write it this way because it's easier for you guys. But there you go. Once you have that, you should be done. That will be the derivative using the quotient rule. All right, we're going at a pretty good pace. Let's try some other problems that don't use the product or quotient rule. Differentiate the following log function. This one's got a root. And you guys know very well, anytime you have a root, that means you'll have to rewrite your function or rewrite the root as the power of 1/2, where the 2 comes from the root, the 1 comes from the power of the inside. And if you look at this, if you rewrite it this way, this is your q. I got parentheses with the power. That means I got to use the orange peel rule, where the 1/2 is the orange peel, the ln x squared is the slices. So let's go ahead, let's do the orange peel rule. Okay, here, my orange peel. To derive it, I'm going to multiply the 1/2 to the front. And then my new power, I'll have to subtract 1 or subtract 2 over 2. And that's going to give me a power of -1/2. Now inside the parentheses, you will still have natural log x squared. We do not derive the natural log just yet. Okay, there's your orange peel. Now we can derive the slices. For your slices, we need to derive natural log of x squared. And just like any natural log, focus on what's in the parentheses. So set up your fraction. On top, you'll derive x squared to get 2x. On bottom, you'll put the original where the original is x squared. Go from there. To make things easier, I'm going to go ahead and simplify the slices. I'm going to take out an x top and bottom. So that's gone. And that's going to become x to the 1, which will just be 2 over x. So the 2 over x will be our slices. Okay, we got our orange peel, we got our slices. Now let's multiply these together. And it looks like right now the only two things we can multiply are the 1/2 and the 2 over x. So let's go ahead and multiply those. So on top, 1 times 2 will give you 2. On bottom, the 2 times the x will give you 2x. And that's still going to be multiplied by all of this. Natural log x squared to the power of -1/2. And of course, some of you recognize, oh, I can simplify the 2's here. So let's go ahead and do that. Simplify the 2's, 1 in bottom. That's going to give you a 1 on top, x on bottom. And that's still going to be multiplied by natural log x squared to the negative 1/2. Now, some of you might be thinking, okay, we've done the derivative, we're done here. However, look at how we started. We started as a root, which means we need to end as a root. So let's fix our problems from there. Or let's rewrite this as a root. Well, to start off, we got a negative power. And to make that positive, we're going to have to flip that to the bottom with the x. So in other words, the 1 will be on top, the x will still be on bottom, but the x will now have a friend. The friend will be natural log x squared to the power of positive 1/2. Hang on, let me rewrite that a little bit better. There you go. Basically, the natural log x just got flipped to the bottom of the fraction. And then last but not least, you can rewrite this using your roots. On top, you'll have 1 on x on bottom, and the x will be multiplied by square root of ln x squared all to the power of 1, where the 1 comes from the power. But of course, you guys know you don't really need to write that power of 1, so you can just leave that alone. Oh, sorry. Nah. And you can just leave it like this. Square root of natural log x squared. I don't like that natural log. Let me rewrite that. So x times square root of natural log x squared. All right, and that's how you do orange peel rule or the chain rule with natural logs. There you go. So now I want you guys to try another example on your own. Go ahead and pause the video and give this one a shot. Then resume the video and check your answer. Okay, you should have resumed the video by now. Let's go ahead and see what we get with this one. So for this one, we'll still have the natural log of x on the inside, but we have a cube root this time, which means if we rewrite it, it means it's going to have a power of 1/3, where the 3 is the root, and the power comes from the power of 1 here. But you guys already knew that. So just leave it as 1/3. And just like before, you got giant parentheses with the power, so we're going to treat that like an orange peel. All right, let's do it. So orange peel, let's derive here. Multiply the 1/3 to the front, and then parentheses, subtract 1 from your new power, or in this case, subtract 3/3, which will give you a power of -2/3. And on the inside, you will still have natural log of x. You do not derive the natural log of x, not yet. And then, now you can do the slices. And the natural log of x is your slices. And just like before, to derive the natural log, just focus on the inside. So derive the x, and that will go on top, or the derivative of x is 1, and then on bottom, you put the original, and the original was x. Okay, and the 1/x can't be simplified, so we're good to go and simplify the rest. Okay, now we can multiply the orange peel and the slices. In this case, so far, the only things we can multiply are the 1/3 and the 1x. So multiply those, you'll get 1 on top, and then 3 times x will give you 3x on bottom. And all this still be multiplied by natural log of x to the power of -2/3. And the 1/3x, that can't be simplified. So we just need to take this part and rewrite it as a root. first things first, we got to make this power positive, so we're going to flip it to the bottom. So let's go ahead and rewrite that over here. On top, we'll have 1. On bottom, we'll have 3x. But now the 3x will have a friend. It'll have natural log of x to the power of positive 2/3. Okay, so now the power is positive. Now we can rewrite our root. So 1 over 3x, that's still a thing. But now the 3x is going to be multiplied by cube root of natural log of x. The natural log of x is going to have a power of 2. So raise that to the power of 2. So there you go. That's basically your answer. If you decide to write it this way, so 3x, give me a second. So 3x times cube root of natural log x. But if you decide to take this square and squeeze it in the middle between the natural log and the x, that is also acceptable. Because again, this notation and this notation mean the same thing. If the power here was inside the parentheses with the x, that is something completely different. Just wanted to point that out. So either one of these is acceptable. I will take either or. All right, and that's your chain rule examples. I just got maybe, I think, 3 more examples to cover with you, and then we'll be done with this video. So let's hop to it. The next example is actually a pretty easy example compared to the others. It's just another simple orange peel rule. So in other words, you got this, you got parentheses, and you got a power. So do your orange peel. So orange peel rule, take this, multiply it to the front, that'll give you 3, and then subtract 1 from that power, which will give you squared. And the natural log of x doesn't change, not yet. And then multiply that by the slices. In this case, the natural log of x will be your slices. And even though there's no parentheses here, it's still natural log of x. I think the math gods just got lazy, and apparently they wanted you to assume that there's parentheses there. But anyway, derive it like you normally do. Derive the x, which will give you 1, and then divide by the original, which is x. All right, there's your orange peel, that's your slices, and now you can simplify. And in this case, we can multiply the 3 and the 1x. I'm going to rewrite the 3 as 3 over 1, which will make it easier to multiply the 2 fractions. So on top, 3 times 1 will give you 3. On bottom, 1 times x will give you x. And that will all still be multiplied by all of this. Natural log of x all squared. And, well, you don't need to flip anything because there's no negative power. You don't need to rewrite it as a root because, well, there never was a root to begin with. So once you're here, you're kind of basically done. But, of course, if you want to rewrite it so that this power is squeezed in the middle, you can do that. Again, these two mean the same thing. And there you go. Piece of cake. All right, a couple more examples. The next one, we're going to be doing derivatives of natural logs with trig functions. Now, some of you are probably wondering, Ms. Schulin, why is there absolute value bars here? The reason why those are absolute value bars is because that's protecting the natural log from becoming negative. Just out of curiosity, if you got a calculator nearby, or if you got an online calculator you can look up, I want you to type in, what does natural log of -1 do? What does that give you? Natural log of -1. Do you end up getting a domain error? If you do, that means natural log is actually kind of limited. Because the thing is with natural log, this number inside the parentheses, it can never be negative. If the number inside the natural log is ever negative, it will give you an undefined answer. So that's why we have a domain error. And that is also why we have absolute value bars here, to prevent cosine from ever becoming negative with the natural log. The derivative, however, the derivative can be negative. It's just we can never have a negative inside with the natural log, because then our calculator will get cranky and no one wants that. So just wanted to point that out. But anyway, moving on. So remember, we basically have to look at the blob on the inside. And again, we just have to derive the blob, and that'll be on top, and the bottom will be the original blob. And of course, this probably means you're going to need to remember your sine-cosine loop. So remember your sine-cosine loop. Sine, then cosine, then negative sine, then negative cosine. And the way this loop works, that if you want to find the derivative, you take the next one down. But if you want to find the antiderivative, you take the one above it. But for us, we want the derivative. So in other words, if you want the derivative of cosine, you got to go to cosine and take the next one down. So the derivative will be negative sine. Then on bottom, the original. And the original was cosine. And that's it. So basically, if you get to this point, I will accept this answer. But for those of you who plan to go on to higher mathematical classes in college, you might actually want to try and simplify this further. If some of you remember from your trig class last year, sine divided by cosine actually simplifies down to another trig function, and that is tangent. And of course, negative sine means this will be negative tangent. I will accept either or, but if you're going to college for mathematical or engineering classes, you might want to get in the habit of simplifying it down to that. And if ever by any chance you get cosine on top instead of sine, that's going to become cotangent. You might need to remember that. If it's sine on top, it's tangent. If it's cosine on top, it's cotangent. You might need to remember that. But anyway, that basically takes care of that one. Now the last example, this one might make you feel a little uncomfortable. The natural log of the natural log of x squared. Some of you are freaking out. 2 natural logs. Does that mean I have to do that rule twice? Do I have to do derivative of the top and the original of the bottom and then do that again? What? What am I supposed to do here? What? Okay. The best way I can describe it is that some students are confused about which natural log to look at. Which one should they really be focusing on? And the one you want to be focusing on is the one on the outside. So in other words, what we're going to do, we're going to derive this natural log. And this natural log is going to have this as its blob. So in other words, natural log of x plus squared is going to be the blob. And remember how I showed it to you guys. Basically, again, anytime you do a natural log, you're going to have some sort of blob inside those parentheses. And the way that it works is you are going to derive that blob and then divide by the original blob. And in this case, this natural log matches up with this natural log. And then all of this, the second natural log with the x squared, that is going to be our blob. So just think of it that way. Natural log x squared, that is our blob. So using that rule, let's go ahead and do this stuff. So, let me go ahead and use green. So I'm going to set up this fraction. I'm going to go ahead and do the bottom first. The bottom says I'm supposed to have the original blob. And my original blob is right here. That's my original blob. My original blob is going to be natural log x squared. Now on top is how we're going to derive the blob. Or in other words, we're going to take this blob, natural log x squared, and we're going to derive it. And the way that you derive it is exactly how you've been doing it the past 10-ish slides. Take the inside and write a fraction. So on top, you'll derive the x squared to give you 2x. On the bottom, you'll get the original, which is x squared. And of course, if you simplify that, that should simplify down to just 2x. So this is the derivative of the blob. So this is what's going to go on top of the fraction that we have in green. So in other words, if you follow that notation, this is what our final answer should look like. Whew. Now some of you are probably freaking out. They're like, Michelle, that does not look pretty at all. We got a fraction on top of a fraction. That looks disgusting. But never fear, you can rewrite that. So let's think of it as we're taking 2 over x and we're dividing it by this natural log. So in other words, 2 over x, and we're going to be dividing it by this. Divide that by natural log x squared. Now, if you rewrite it that way, it looks a little bit more pretty. But now that we have it rewritten this way, this helps us a bit. As you remember, I can change that division to multiplication, but on one twist. The twist is that I need to flip the second part. Rewrite that as 1 over natural log x squared. And once I have that part, give me a sec. And once I have that part, now you just need to multiply the top parts and the bottom parts. On the top part, now you'll get 2 times 1, which is 2. On bottom, you'll just have x times natural log x squared. And sadly, the x and the x squared cannot multiply because one is with natural log, the other is not. So you're just going to leave that as x times natural log x squared. So that one was kind of tricky, but you've got to think of it this way. Think of it as you're always just going to do natural log of the blob. Don't get distracted by the fact that you have 2 natural logs. Focus on the outside. The inside natural log will be the blob, and you'll have to just use what we've been talking about to help you go through it. If you have any questions about that particular problem, if you want me specifically to double check it before you submit it into Google Classroom or email, again, just email me. I can go ahead and take a look, but that is up to you. Anyway, that is it for the introduction of natural logs. Here is the assignment to practice some more problems on natural log. And again, if you have any questions or concerns, you can just email me. With that said, I hope you guys are having a wonderful time. Stay healthy. Peace out.